the general gist of this tube is all about working smarter, not harder, with your power series. In other words, what we're going to do is construct new power series from simple power series, like geometric series or something like that. So I'll show you how to do some basic problems. There aren't any X-rated ones this week, so we'll have a look at just the basic idea. So. Okay, remember, if you can't see, you can turn one of those lights off. You're not going to be bothering me if you do that. All right, so this is part A. X plus 1 e to the x. So our function g is defined in the following way. How can we build a power series, I guess, for g of x about x equals 0? Any ideas? I guess. Well, I guess Cn's a sequence, whereas e to the x is like a function. There's no n in e to the x. But I guess as a first thought, what is the power series for e to the x about x equals 0? The Maclaurin series, right? We know that. So the Maclaurin series, which you should know straight off, is just this. So it involves powers and factorials, right? Now, I've made a bit of a claim here that this function and this series are equal, right? But for what x values do we actually have equality here? For what x values does this series converge to this function? Anyone know? Huh? Well, all values of x, right? Okay. So you can verify that by using ratio test. Okay, so to get the series for g of x, from this, let's just multiply the series by x plus 1 in brackets, right? It seems logical. Now, this guy here's got nothing to do with k, so we can move him into the sum if we want. And there's our series for g of x. So we didn't have to compute anything, really. It's just building a new series out of a known series. So it's pretty straightforward. Let's move on to C. Here we have our function g of x defined in the following way. And we're asked to come up with a power series for this function, g of x. Now, I think we're given a hint in this one. We are using a power, a power series. This is a special power series known as the geometric series, right? Now, the first question is, if we're going to use this series, this special series, what x values is this series valid for? Down here. One's definitely out because that's not defined. Right. So it's not. You have to be careful with these series. So here. Now you can come up with this interval either via the ratio test or just looking at the partial sums of this series here. Okay, it's back in I think grade 10, grade 11. Now the point is that if we're going to do calculations with this special series, we're always restricting ourselves to this interval. Okay. So that's important. If we're going to work with something, we need to make sure that all the calculations we do with it are well defined. So to ensure that happens, we're restricting our x values to this interval. All right. So any ideas how we can form the series for G from this boxed series? Differentiate. Right. So let's call this, yep, you guessed it, star. So on the left-hand side, we're going to get something like 1 minus x all squared. Now that's equivalent to G, right? So all we really have to do is to go through here and differentiate term by term. Now, sometimes with these, I like to actually write out the first few terms of the series and then just differentiate and then collapse it back into a series. With this one, I'm not going to do that. Okay, so I'm just going to differentiate. So the first term's going to go to 0, and I'll get something like this. Okay. Now, what values of x do we have this equality for? Okay, what values of x? Well, right, between -1 and 1, right? So again, pretty simple. All we did was use the geometric series, which is something you saw at school, to get another result. Has anyone seen anything like that method before? Okay, all right. If you haven't seen it, that's okay. All right. Yes. You can. Okay, so you can multiply two power series together, but you're limited to the smallest interval of convergence out of the two of them, right? Oh, yeah. Oh, so you mean down here? So you mean get the series for 1 on x minus 1 and yes, it's going to be messy though. It's going to be messy to sort of put it back into one series. But yes, you can multiply power series together. They do it as long as they converge. They obey the rules of algebra. Okay. All right. Let's have a look at 44. So are you guys okay with the, can you read okay? If it's not, then you need to, we can shut off one of the lights. That might make it better. Everyone see okay? Okay. All right, so in 44, you're asked to use, again, a geometric series. So let's call this star. And we're asked to form a power series for 1 on 1 plus x squared. So I'm doing part B now. Any ideas on how we can form the power series for 1 on 1 plus x squared from that? Yeah, substitution. So what we could do up here is replace x with minus x squared, right? So all right, so we're going to obtain the following. So the left-hand side is going to become 1 on 1 plus x squared. The right-hand side is going to become minus x squared all to the k. And if I want to, I can expand that bracket and make it a bit prettier. Now again, that's only valid for x between minus 1 and 1, right? Because that's what the original series that we did our work on was restricted to. Okay, so part C uses part B to obtain a result. So we're asked to form the power series for tan inverse x about 0. So any ideas? Yeah, integrate part B. We know that if we integrate this interval of convergence, then we can swap the integral and the summation. Now that's a big step. That's a huge step. There's a lot of analysis in that. Okay, so tan inverse x is just this integral here. Now, because we have the convergence, and this is a huge, huge step, it means I can switch the summation and the integration, okay? That's a huge step. Now, you can, if you want to, expand the bracket here and just write out some of the terms, integrate them. I'm not going to do that. Now, the first thing I'm going to put in my constant of integration. And then when I integrate each of these terms, I'm going to get something like this. Now, how do I get my constant of integration? Anyone know? Yeah, so if I sub in x equals 0 in this equation, the left-hand side's 0, the right-hand side's going to be 0, and I just get c equals 0. So our series if I can squish it in, is this. Okay, so this is our power series for tan inverse x about the point 0. Okay, all the series I've been dealing with here are about the point 0.
Why you subbed in x equals 0?
Well, that's one of the reasons. I mean, this is certainly well defined for x equals 0. So, yes. That's a good question. Okay, all right. So that's how you can build new series from old series. Can I just have a show of hands? Who's seen, like, who actually remembers the geometric series from school? Just maybe vaguely. Show of hands. Okay. Anyway, all right. Let's go into something a little bit more in depth. This is 45, I think. All right, 45. Anyone done it? You've got the following function. You know? Yep. It looks like you would. It looks like you would. Yes. Yeah. Yeah. So Taylor series are a special case. So it'd be a Maclaurin series in this case, right? So Maclaurin series, Taylor series are a special case of power series, right? Where the derivatives in. Yep. But why? I mean, you don't have to do any. Like here, you don't have to do any real calculations. Okay. So. Here we've got a function defined like this. Now, x squared times sine of x cubed. Now, what this question's asking you is to perform an analysis on this using power series and show that this function has a stationary point at x equals 0, and then classify the stationary point. That's what it's asking you to do. Now, sort of just intuitively, let's say this function has a stationary point at x equals 0. It has a turning point, right? Who can tell me, without doing any calculations, what the turning point should be? Without doing any calculus whatsoever. You should be able to do it. So suppose it has a turning point at x equals 0. What is the nature of the turning point? Ah, yeah. So here's a good. You guys probably know this from school, but let me just remind you, right? X squared is an even function, right? The sine function is an odd function. If you multiply an even function and an odd function, you get what's known as an odd function, right? So an odd function looks something like this. It goes through the origin, and there's some, you know, if you twist the graph around here 180 degrees, you get the same graph. Now, if this function's odd, right, and it has a turning point at 0, it's got to be a point of inflection. It's got to be a point of inflection. Okay? So is
that your answer?
No. well, it's my common sense answer. Okay? And if it has I guess a turning point now. That's a skill that requires no calculations that you should be able to. I mean, did you guys see that at school? Odd and even functions? Okay, all right. Well, it's something that's gold. Okay. However, let's get back to the program and see what they're trying to actually get us to do here. Firstly, they want us to calculate the power series for sine of x, and then use that to get the series for sine of x cubed, and then you can use that to get the series for f, right? The power series about x equals 0. So we know. Okay, so is the following. Now, can anyone remember, bless you, can anyone remember what values of x this is actually, when do you have the equality? Is it all values of x? It is. Okay, you can use the ratio test to test that. So you should know these special expansions and their domain of definition, right? That's something that can really do good things for you. So what's our series for f of x? Well, it's just we replace x with x cubed and multiply the whole thing by x squared.
Could you start with cos and then differentiate it?
Interesting. Yes, you could. Yeah, that's interesting. Yep. So let's just fix that up, I guess. So bring the x squared in there. So what are we going to get? We're going to get something like x to the 6k plus 5. So I'm just going to write out a couple of terms of the series just to give us a bit of a slight feel for it. All right, so that's our power series about x equals 0. Now the next thing they want you to do in this question is show that 0 is a stationary point, right? So yeah, so let's differentiate and see how it goes. Okay. So if I differentiate, say, my power, I could differentiate up here and then show that, the derivative 0 adds 0. But let's just use this one. If I differentiate here, what's going to happen? The lowest power is going to be power 4, right? So, of course, it's going to be 0 at x equals 0. Right, so if I just differentiate this, I'm going to get x to the power 4 in all higher order terms. And then if I sub in x equals 0, I just get 0. Right. Because we're differentiating. Oh. Yeah. So differentiating. Yep. So. I think it's from the series. How's that? From the series in A, okay? Because you could get confused with that, right? Anyway, all right. So the last thing is, let's classify this point, the stationary point or turning point. Okay. Now we know we absolutely know that it's a point of inflection. Okay, because the f's odd. Now, if you try to go through here and take a second derivative, right, and plug in x equals 0, what are you going to get? 0. So the second derivative test absolutely fails. Now you might think, well, let's just look at the derivative on either side of 0. Well, you've got a nasty series there, so I don't see how that's going to help you. I guess critical point. So the second derivative test fails. but f is odd. So what do I mean by odd? I mean f of x equals minus f of minus x. Okay? Okay, so when I say odd, I mean, you know, something like, oh, it's a bad picture. But the point here is that if you rotate the graph 180 degrees, you get the same graph. Okay, that's the basic idea. Questions? Okay. Let's have a go at 47. This is an interesting question where they've defined a function via, I guess, an integral. So you can call this the psi function. It's still good, isn't it, man? It's still good. That's good enough to eat, isn't it? No? Does it sting? Anyway, don't worry about it. All right, so our function is defined in the following way, the psi function. Now, this little f of t is defined this way. I did have a picture somewhere of this, but it seems to have disappeared. Anyway, let's have a look at the function. F of t is continuous, okay? So they've sort of, it's got a removable, I guess if you cover that up, it's got a removable discontinuity that you can just plug. So it looks something like this. What they want you to do here is calculate the series for psi of x. Now, before you do that, they're asking you to show that pi is a turning point or a stationary point of the function psi. Now, to show that x equals pi is a stationary point, let's differentiate this and show that it has a 0 at x equals pi, right? But before we do that, we better check, if we're going to use the fundamental theorem of calculus that we know here, we better check that this is a continuous function, right? So it is. It is a continuous function. So the fundamental theorem of calculus, the FTC. So if I differentiate now at x equals pi, right? This is going to have a 0. So if you f of pi is 0, because we're using this definition up here. So we've got to have a turning point, some sort of Okay. Next thing is to classify the point, right? Is it a local min, a local max, point of inflection? Well, in this case, you can use a second derivative test. So if you take the second derivative, just from here, and plug in x equals pi, so this is the only one you're worried about, you'll get something like this. It's negative. So you know that the turning point must be a local maximum, right? All right. So okay, so we've jumped through the hoops. Next thing is let's calculate the power series for the psi function about 0. So essentially what we do is we look at the sine function here, look at the expansion, and then see if we can get some nice cancellation. Yes?
Does it matter whether you put when t equals pi or when x equals pi?
Well, I guess t here, that's a good question. T here is the dummy variable, right?
Yeah.
And x is the independent variable. Okay? So, yeah, so I would say x equals pi here. Yeah. Okay. So for part B, let's consider the following, and let's calculate, well, I guess we don't even need to calculate it. We can write down the expansion for sine of t about 0. Okay, so sine of t is just t minus t cubed on 3 factorial. So we keep on going with the odd powers and the odd factorials. So now, because we're not at 0, we can cancel off the t's, right? So up here, I'm going to get 1 minus t squared on 3 factorial, etc. And down here, I'm still going to get 1. Now, look closely. These two definitions are the same for t equals 0. So I can just bring them back to the following. This covers both cases, t equals 0 and t not equal to 0. Okay? However, we want the power series expansion for psi of x, not for f of t. So what we're going to do is just integrate. So we've got to go back to our definition. We're going to put our power series in there and just integrate it from 0 to x. Okay, so let's put in our power series, which is something like this. We just calculated it. So let's just do the integration, right? So now, the constant of integration. Again, plug in x equals 0, you're going to get c equals 0. Oh, hang on. No, you don't need this. You don't need the constant of integration. Anyone know why? It's a definite integral. Oops, sorry, YouTube. All right, that's it. Okay. All right, let's do something. Okay. There is a part of that question where it says, okay, estimate psi of pi. So when x equals pi, we want to estimate this to an accuracy of 1/100th or something like that, right? I'm going to leave that for you to do. I'm going to leave that for you to do because there's an ODE question that I want to do, and you know that I love ODE, right? All right, so this is something that you'll see in second year a bit more. It's called the method of Frobenius. So let's consider the following ODE. Now, the problem with this ODE is that it's linear, it's second order, but the coefficients are non-constant. Okay, so we don't know how to solve this. Okay, so that's the important part. What we're going to do is use power series to solve this. We're going to assume that the solutions to this problem are in the form of a power series. Okay, now that's a big assumption. Okay, but we'll work under that assumption. Now, what you want to do is write the right-hand side as a series. You're going to assume y is a series, so the derivatives are also going to be series, and then you're going to equate the coefficients in all these series. So the first part is to write down the series for this. So we know e to the x is just this. And so if you just take out the first term and move it to the other side, you'll get this. So part B says assume the solution to our ODE is in the following form. Now, if we can determine some sort of setup for A sub k, then we've completely determined our solution. So we're assuming it's a power series, and what we're going to try to do is find these coefficients, these A sub k's. Once we know those, we have the whole series, so we know our solution. Okay, so we're looking for A0, A1, A2, blah, 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 blah. Now, what I'm going to do is take this general form of the solution, differentiate once, twice, and sub it in, including my part in A, into this starred series. Okay, so it's going to get a bit messy, but so if I differentiate, I'll get something like this. So if I, again, if you can write out these if you want to. You're going to get A1 plus 2A2x plus blah, 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 blah. And the second derivative is going to be something like this. Okay, so if I differentiate again, I'm going to get something like that. Okay. All right, so let's take these four, I guess we only need 3 of these things, sub them in here, and then we're going to equate the coefficients. Okay, so on the left-hand side, I'm going to have x squared times this plus x times this equals this series. Okay, so it's a little bit messy, but okay, so that's my first term, my x squared y double prime. That's my second term, x times y prime. Yep. Okay. Now, to equate everything, what I'm going to do is get these lower sums. So here I start at k equals 2, right? If I put this in, I'm going to get x to the k in here. If I put this in, I'm going to get x to the k. I've already got x to the k there. So the powers, the corresponding powers, are going to be all the same. The only thing that's different about these sums is that I start this sum at 2, I start this sum at 1, and this sum at 1. What I'm going to do is expand these 2 things here, so that I've got all the summations starting at 2, right? So I'm going to take the first term out of this sum and the first term out of this sum, right? And then I'm going to be left with the following. So it's a little bit messy, but let me show you. So I've used, so the big brackets mean is the second term, which I'm taking the first term out of the sum for. Yes. Oh, hang on. X to the k. Sorry. So this is x to the k here.
So why not put everything start with k equals to 1?
Because these sums aren't defined at k equals 1.
But the value is equal to k equals to 1.
What? I mean, at k equals 1, this is 0, so you get no information from this sum.
It's something, if you put k equals to 1, then the answer won't change because there is 0. So if you add something with a sum with a 0.
Yeah, well, I'm sort of going up to the highest number that I can. So I saw that this is starting at k equals 2, this is starting at k equals 1. So I'm going to take out the sums and start them at the highest number down here. Okay? All right, so what have I got that's left over? Because I've got equality here, this coefficient has got to equal this one, right? So what do I know about A1? It's going to be 1, right? So you're just comparing the coefficients now. Because we have equality, the coefficients on this side have got to equal the coefficients on this side, right? Now, if I sort of join this sum up with this sum, then what do I get? I've got a common factor of a sub k, and over here I've got 1 on k factorial. So I can just clean up here, and I'm going to get k, a sub k, equals 1 on k factorial. So a sub k is just 1 on k times k factorial. Now I already know what A1 is, so oh yeah, oh sorry. Yes, k squared. Thank you. Sorry, YouTube. Big props to Manav for that one. No, that's all right. Just giving you props. Okay, so what does it mean? What does it mean? So I've found my a sub k. So I can go back now and write a definite a sub k in there, and I've got my solution. Sorry. Okay, so it looks a bit messy, but that is your solution based on the assumption that your solution was in this form to start with. Now that's a huge assumption. Okay, it dates back to the method of Frobenius. Okay, and that's something you'll see a little bit in second year if you do more maths.